Okay, let's talk about chapter 4. Differentiability on R. Okay, so remember that we actually have all the concept, but in the calculus, we just didn't prove them. We take them for granted. So in this class, we just go over all the concepts, but we are going to feel the proof. Okay, so first, 4.1 is the derivative, the section. Okay, so we all know what is the definition of derivative and what is differentiability. So now let's first give the definition. We say a real function f is said to be differentiable at a point A in R if and only if f is defined on some open interval I containing A and f prime of A is the limit h approaching 0, f a plus h minus f a over h, or sometimes remember that you always see this one, x approaches a, fx minus fa, x minus a. This is symmetric form. Okay, if this limit exists and f prime of a is called the derivative of f at a. This is f prime of a is the derivative of f at a. Okay. So we all know that the geometric meaning of this definition is that when you have a point A here, and if you have x this place, and you connect x, this is point A f a, x f x. There's a line through those 2 points. This is called a secant line. And this fx minus fa, x minus a is a slope. And when x approaches a, the limit gives us the slope of the tangent line. Right? So that's the concept. We all know that the limit will give us the slope of the tangent line. And you have the point A, fa, then you can write the equation of the tangent line. That's a geometric meaning, right? And also, you can consider this as the rate of the change consider this as the rate of the change over AX or XA. So be careful here. X is not always on the right side. X can be on the left side when X is less than A. So it can be on the left side or right side. Okay, then the limit gives us the instantaneous rate of change. Right? Instantaneous rate of the change of f at A. Remember, this instantaneous rate of the change, for example, the velocity. The velocity. Remember, the velocity is instantaneous rate of the change of the displacement. Right? Velocity is instantaneous rate of change of the displacement. So this is explanation in geometry. This is explanation in physics, the rate of the change, the velocity. And from this geometric explanation, we know that the graph of y equal to fx has a unique tangent line at a point a f of A. It has this unique tangent line if and only if f prime of A exists. Because when f prime of A exists, you can have the slope. Without slope, you cannot get the tangent line, right? So this is the relation, again, the relation between the tangent line and the derivative. And if you see here, this derivative is always defined in terms of an open interval. If you do not have an interval, then there's no way to define the derivative based on the definition. If f is it's not just differentiable at one point. If f is differentiable at each point, in a set E, then f prime is a function on E. So it's called the derivative function, right? F prime becomes function because each point you can define f prime of A. So every point you have a derivative. Every point you have a derivative, you have a derivative function, the derivative function. The derivative function. Okay, so for the derivative function, because this concept was developed by many mathematicians, so sometimes they use this type of notation, sometimes they use not that type of notation. Different types of notation have different applications or the reasons, so we have several ways to write the derivative. So you can say the derivative of f at x, dx of f. Or you may see df over dx. It's like the instantaneous rate of the change, difference of f over difference of x. Or you may have the notation like this, but remember you put the parenthesis f2 parenthesis 1, or just f prime. Okay, so you have several definitions. So not definition, the notation, several notations, they all mean the derivative function. And also, if you have y equal to fx, then we also write y prime dy dx as f prime. Okay. We also write y prime dy dx as f prime. And you see, from a differentiable function, we can have a second function, another function f prime, and possibly the f prime is also differentiable. If f prime is also differentiable, it may not be the case, but if it's also differentiable on E, we will have, or we can have, the derivative of f prime, which we write the prime of prime f double prime, the prime of prime f double prime. Okay. And we can continue this if possible. So we have the higher order derivative. Higher order derivatives, so it's better for us to use this notation. You see here, that's why we put 1 here. This is, we call the first order derivative. Higher order means you have the previous order derivative, nth order derivative, and you differentiate again. The second derivative is the derivative of the first derivative. This is also called the first derivative. And this is called the second derivative. And you may have third derivative. Third derivative, you can put triple prime. But fourth derivative, start from the fourth derivative, you will not put 4 primes. You will just get the f to fourth derivative, the fourth derivative f. Okay, so you don't write the 4 primes. But third derivative, for the convention, we still write the triple prime. And like this notation, system notations, so you see here, if we have the nth derivative, well, without the dx super n of f, it is equal to the d to n f dx to n. So be careful about the position of n, or you can write the nth derivative, or you can write nth derivative y, if y is fx, or the dn y dxn. The reason we put n at a different position is the following. So remember, you see, dy dx, it looks like we put d dx, we apply d dx to y. It looks like this in philosophy. And then if this is the first derivative. If we want to get second derivative, we're going to put d dx to the d dx of y. So that's why you see here dd is a d square. Dx is actually you have dx square, and then you put a y here. So that's the reason you have different position for the same quantity. Okay. Okay. All right, so that's the notation. It's first order, second order, higher order derivatives. Now let's see a characterization of a differentiable function. What is a characterization? So first we define for x not equal to a, we define capital F of x as fx minus fa over x minus a. We need x not equal to a because it's a denominator. and it's called the chord function. Actually, this is a average rate of change. Well, the name is not standard. It's called the chord function. Just have the name in this book. Okay. The theorem is the following. A real function f is differentiable at some point a in R, if and only if there exists an open interval I and a function capital F from I to R such that A in I, so the open interval contains I, F is defined on this open interval, capital F is continuous at point A, and little fx is capital Fx times x minus A and plus Fa. Okay, this holds for all x in I, in which case means if it is differentiable, capital F of A is F prime of A. F prime of A. Okay, so this is the case. So here, this one, you will see that when x is not equal to A, you move Fa to the left side and divide x minus A, you will get Fx is actually like this. But in the statement, we don't actually require Fx, capital Fx have this form. We just say there exists a capital F. Okay? Anyway, let's see the proof. The proof is just routine check. Okay. So first of all, when x is not equal to A, when x is not equal to A and the capital F is equal to Fx minus Fa over x minus A. This always exists. So this formula is equivalent, satisfy. So these two things actually are the same thing. We say satisfy or they are the same thing. Okay, okay, so that's one thing we observe, you have something. So now let's see proof you have two directions. Suppose Fx is differentiable at A. If Fx is differentiable at A, then this limit exists. This limit exists, of course, capital Fx is continuous at A. how do we get capital Fx is continuous? We just define Fx as a value of it, okay? By capital Fx is continuous at A by setting capital Fx as a capital F of A as the limit of it. Remember that whenever the limit at a point exists, that point is at most a removable discontinuity. Okay, so when the limit then x equal to A is at the most, the worst case, at the most a removable discontinuity. So it's not bad. Whenever you have the limit, it is almost equivalent to the continuity. Okay. Okay, so we prove that Fx is continuous, and also Fa prime is capital F of A, because this is F prime of A. F prime of A. Okay. So from continuity, we get a continuous function, capital F, satisfying all these conditions. If capital F exists and little f is capital F of x times x minus a and plus f of a, then we just compute the limit x approaches a, fx minus fa, x over x minus a is just a limit x approaches a, capital F of x, and we know that capital F is continuous, so it is equal to f of a. Exists. So f is differentiable at a with f prime of a equal to capital F of a. F prime of a is capital F of a. Okay? So you can see that this capital F of x is almost the slope function, but this slope function only works at a. If you change it to another point, this capital F will not give you the slope. Only at a, it gives you the slope. Alright? Only at a you have a slope. That's a one characterization. You can write it almost a linear function. What is a linear function? Ax plus b, mx plus b, whatever. So here fx, it plays as a coefficient, but it's not a coefficient, it's a function. So it's almost a linear function. Okay. So second characterization, this is the first characterization. Second characterization says this is a the true equality. And second characterization is about linear approximation. So we set up the linear approximation. What is a linear approximation? We are saying the difference can be approximated by a straight line. Through the origin. Straight line through the origin, mx. Okay? Straight line through the origin just means mx. Okay, so what is this the linear approximation? Let's see. Let f from R to R, then f is differentiable at A. We always say, just say at a single point, if and only if there is a function t of the form t of x equal to mx. See, this is a linear approximation, such that, okay, so fa plus h minus fa, this is difference. It is approximate. This difference is approximated by t of h. Approximation just means this is not exactly 0. If this is exactly 0, this it becomes a true linear approximation. True linear function. Approximation means the ratio is equal to 0. The ratio is equal to 0. Okay. Compared with h, it will be tiny. This result is equivalent to the result in the book. In the book, they put absolute value. They put absolute value. You can prove that. Remember, we can prove this. You have a function. We say a function. F is a function. Real function, real valued function. Then its limit is 0 if and only if the limit of absolute value of fx is 0. Okay, so these two things are equivalent. You put or you do not put absolute value. If the limit is 0, you have the same thing. But the advantage of formula with absolute value is that you are talking about a positive number. For the positive stuff, you can use squeeze theorem or other stuff very easily. Sometimes if you only have fx and compute the limit equal to 0, you need a little bit of trick. So that's why we always put absolute value, so that we're talking about the limit of positive function approaching 0. That's equivalent to the limit without absolute value. Okay, differentiability. F is differentiable. At A with m equal to f prime of A. Okay, let's assume you have a differential function with a slope with the f prime of A m. Then let t of x to be mx, this t of x to be this. Then what we have? We have the limit x approaches this h approaches 0, fa plus h minus fa minus f prime of a times h. Remember t, what is t? T of top, t has a form mx, so mx over h. Okay, so this is equal to the limit h approaches 0, fa plus h minus fa over h and minus f prime of a. Because this is a constant function, the limit of a constant function does not depend on the limit of function. The limit of constant function does not change, and this part is has a limit. Remember, we assume f is continuous, is differentiable. So this part has a limit. So you have the difference rule about the limit. Okay. this is f prime of a minus f prime of a equal to 0. And check here, this part we didn't put ops value. We didn't put ops value, but this one is equivalent to this. Okay, this is equivalent to it. On the other hand, conversely, assume we have this. Then we're going to compute h approaches 0, fx, f a plus h minus fa over h, and then we subtract m. This m is from the tx equal to mx. Well, this is equal to again, we apply the difference rule about the limit. This is a limit minus a constant number. Constant number, you can move it into the limit. You have this. And this, again, this condition is equivalent to the previous condition. The difference, the limit is equal to 0. So I don't quite get why the speaker put ops value in this place. I really don't think this is useful. I don't think it is useful. It's useless. Okay. So we do need this one has limit 0. This is t of h. Okay. Here is a mh because it's in terms of h, the difference. All right. So this one limit is 0, so it means this limit is equal to m. The limit exists, f is differentiable. At a with f prime of a equal to m. F prime of a equal to m. Okay? So when we have a differentiable function, the difference can be approximated in a small region, can be approximated by the multiple of the difference of variable. Okay. Another common fact, a common fact about differentiable function is that, remember, in the very beginning, we never mentioned about the continuity of the function f. We just say if f satisfies that the limit exists, then we say f is differentiable. But of course, we get this result. If f is differentiable at a, then f is continuous at a. So differentiability means you have a smooth curve. Continuity just means you have a connected curve. So differentiability is stronger than the continuity. The proof is trivial because remember that f is differentiable, then fx can be written like this with capital Fx continuous. Right? And that's it. F is a combination of continuous functions, so fx is continuous. So it's not that difficult. So in other words, if you have a function which is not continuous, then you can say it's not differentiable. Discontinuous function is never differentiable, right? Discontinuous function is never differentiable. But we do have continuous function that is not differentiable. continuous function may not be differentiable. Remember, continuous just means it's connected. Continuous only means it's connected. It does not mean the graph is smooth. So we're going to see the connected graph, but not with a non-smooth function. Not smooth means, a natural way we see there is a corner. So like this. This is a standard universal example about a discontinuous function, ops value function. We always know that this function is continuous everywhere, but not differentiable at x equal to 0. At x equal to 0 is not differentiable. Well, how do we prove it? We can easily see that the limit h approaches 0 from right side, f0 plus h minus f0 over h is just a limit ops value of h over h is equal to 1, and the limit h approaches 0 from left side, f0 plus h minus f0 over h approaches 0 from left side, ops value of h over h. This case, ops value of h is negative h. It's equal to negative 1. So the right limit is not equal to the left limit. Limit does not exist. Then it's not differentiable. So it's a standard one because we all know this, so I go through it very fast. Okay. Okay. So this definition of a derivative is a standard definition, but sometimes the standard definition, and the standard definition means when you have h can be positive, can be negative. In other words, this point should be inside the interval, open interval. But sometimes we have closed interval. Closed interval, it has two endpoints. Endpoints are not inside. So we want to include those two endpoints into the discussion of differentiability. So we have the next definition. What is the next definition? So let I be a non-degenerate interval. Okay, it could be open, could be closed, could be half open, half closed, whatever. Then we say a function f from I to R is said to be differentiable on I if and only if okay, now we define it in this way. Well, this time it's better for us to use x. It's ugly. fx minus fa over x minus a. X approaches a. But when a, for example, is a endpoint, so for example, it's a right endpoint, then x can only approach a from left side. If a is a left endpoint, x can only approach a from right side. So I don't want to discuss the difference. I don't want to write this definition repeatedly. So that's why they put this condition. X in I, the point x in I. So if you have the right endpoint a, then x approaches a from left side, but x has to be in I, so x can only be selected from left side. Okay, if A is a left endpoint, so x can only be selected from right side. So this condition just guarantee that we include the endpoint into the discussion. So fx minus fa, x minus a. And in this case, it's better to use this notation, not use h, because I don't want to say h is, sometimes h is positive, sometimes h is negative, sometimes h can be positive or negative. Okay? So when this limit exists and is finite, we only discuss a finite value for every a in I. Okay, we don't discuss infinite. The derivative cannot be infinite. In other words, we don't discuss a situation when the tangent line is vertical. Vertical in derivative is infinite. Okay. Second part, f is said to be continuously differentiable. Continuously differentiable on I if and only if the derivative exists for each point and the derivative function is continuous on I. So you have a continuous derivative we call original function continuously differentiable. Continuously differentiable. Okay, so for example, if we have fx equal to x to the power 3/2, then f prime, okay, this definition, this domain is over 0 infinity. 0 infinity, it can be because you have square root. Then f prime of x is 3/2 x to 1/2. This one exists on 0 infinity also. Okay, so this is good. This is good. And it's continuously differentiable. But I'm going to emphasize that f prime of x is not differentiable on 0 infinity. It's not differentiable on the whole interval. I'm not saying it's not differentiable everywhere. I just say not on the differentiable over the whole interval, because the derivative of the first derivative, it becomes this. This is undefined at x equal to 0. Only this point give you the bad point. Other points are okay. Only x cannot be 0. So when you have this situation, then you have to exclude 0. You have to exclude 0. All right. So this one is continuously differentiable, but this one is not continuously differentiable over the whole interval. The domain might be smaller. Okay, so we have for each n in the natural numbers, the book uses this interval. Cni will denote the collection of real functions whose nth derivative exists and are continuous. On Okay, nth derivative exists and continues. Nth derivative. So C1 is continuously differentiable. C2 will be the second differentiable with a continuous second derivative. And also we have C infinity. C infinity just means you can differentiate infinitely many times and the derivative are still differentiable. Okay? Okay. We have C infinity. And also we know that Cm I will be included in the Cni if m is greater than or equal to n. And some element, some function, it has continuously nth derivative, but it may not have continuous higher derivative. So we have this inclusion. Okay. Okay, so let's see the example. The example is the following. We have fx equal to x squared sine 1 over x. This is x not equal to 0. If x is equal to 0, by the square theorem, we can show that this has to be 0. And this one is differentiable on R. Differentiable everywhere, but not continuously differentiable. On any interval containing the origin. Okay, so what does it mean? It's not differentiable over the it's not differentiable not continuously differentiable on any interval containing the origin. Well, let's try to check it. Differentiable, we need the derivative. Okay, so derivative, what we have, if x is not 0, for any point not equal to 0, it's just like this. You just use the product plus the quotient, the chain rule. So you will have f prime of x equal to 2x sine 1 over x, and what's that? Next, plus x squared cosine 1 over x times negative x to negative 2. So it is 2x sine 1 over x plus cosine 1 over x, minus 1 cosine 1 over x. Okay, so this is the derivative at x. For x equal to 0, what is the derivative? This is x squared sine 1 over x minus 0 over x. Okay, this is x minus 0 actually. Okay, so this 0 don't care. It's just x approaches 0, x sine 1 over x. Remember, sine x over x when x approaches. The famous, the limit is this limit. The famous limit is this limit, but this one is not. This one is not. Okay, if you flip x to the denominator, the x approaches 0, 1 of x will approach infinity. It's not. Actually, this one is done by the square theorem. This limit is 0. This limit is 0. So you see here, at every point, so f is differentiable everywhere on R. Every place you can find the derivative. Every place you have the derivative. But the limit of f prime of x, you see, 2x sine 1 over x and minus cosine 1 over x. This part has limit of 0. That's fine. Cosine 1 over x, this does not exist. So this derivative function has no limit at 0. No limit at 0, so it's not continuous. So it's just differentiable but not continuously differentiable. So f does not belong to C1 R because it's not continuous. Okay, so that's the example. So here, this is something I wrote when I'm trying to explain. This one is not 1. This is not a 1. This is in 0 by the square theorem. And try to convince yourself why it is 0 by the square theorem. Okay, so let's stop the video at this point, and we will continue the discussion in the next video. Thank you.